All right, welcome to start of the new content for exam 2. So I do have the pacing schedule set up. We're going to take a look at something called the chain rule, which is another technique for taking a derivative. But also at this time, it's a good chance, first of all, I'll have the exams back to you by next Tuesday. I'm still working on scoring them. Remember, I've got a Monday, Wednesday class, so I've got 2 sets of classes to get scored. But I'm sure it's like, I've scanned a few, but some of you will have done very well and you'll be satisfied. Others of you would have liked to have done better. That's fine. But I want you to keep engaged and keep thinking how you can, if you'd like to do better, let's think of how we can make that happen. So first of all, I do a holistic type grading. So if I see improvement, because we will retest on some of this material in the final exam, right? So if you didn't do as well as you'd like, I don't have specifics of this point replaces this point or something, but I do take a look, and if I see improvement, I can make sure that the lower score doesn't replace the higher score, which is later and shows learning. So I do that. So there's a way you'll focus on the learning part and understanding the content and go forward. So part of what I've done for that is I've extended all the homework assignments from the first test until Sunday. So if you haven't finished some of them, you can get some points there, but more importantly, you could go back and maybe learn some of the concepts that you didn't have down before. Secondly, there is so instead of doing quizzes along the way, maybe I have never found them to be all that helpful, but what I do is I do the review. So if you do the review, take a picture, upload it. Many of you have already done that. If you haven't, I put in a 0 grade, but that doesn't mean that's final. That's just to say, hey, there's something missing, because if I don't do that, Canvas doesn't give you any warning, but you'll see, oh, my grade dropped. Okay, you just need to upload your scratch work from the test. People will ask, well, do I have to do every problem? I says, just upload it. I'm not going to even look at it, but I'll see that there's a document that's been uploaded. You should do the reviews as much as possible, and that will help you on the exam. But at the same time, if I've talked with some of you and some in the other class, you may just scan things, and if you understand it, you move on to the so you'll spend more time on certain things than others. If you already understand it, you don't have to. So don't do busy work to try to show me that you've done work. Focus on what you're learning and in your comfort level in doing what we need to do for the exams. Okay. And the other thing is, as we go forward, we'll get into the chain rule. There's going to be some more things that we're going to be doing with derivatives. Some of this earlier stuff, especially like the product rule and the quotient rule, you'll learn them more deeply as we go forward. There wasn't that many. I think there was one question of each on the test for one of those, but we had one day at it. You'll get those down better. So keep making progress. Think about what's been working. Think about what hasn't been working. Try to do less of the things that don't work and more of the things that do work, that help you get to where you want to go. Okay. And you'll see, so as we go towards the next exam will have 11.4 to 12.5, that kind of content. So we've got all that there. There is one other section, 12.6, which is called elasticity. And some of you who are in, let's see, what kind of a elasticity of demand, supply and demand type stuff. Some of you probably have covered elasticity in your business classes. So we introduce how calculus is involved in that. And there's kind of basically a formula. It won't be on the exam. There won't be a question on elasticity on the exam. So actually, I had it in here. I took it out because I felt a little scrunched. We may be able to cover it a little bit. I have a recorded session of it. What I'm going to do is 12.6 will be extra credit. And what that does is, those of you who are a little bit behind, you will definitely do that because you want extra points, right? Those that you are doing well, you'll do it because you do everything anyway. It's just the way things work. So it's probably beneficial just to at least take a look at it. But we'll throw some extra credit. I think they let me, I can't remember the rule, but I certainly have at least 1% of extra credit that I can do in here, and that is under that. So that it'll help, and it'll be a good learning lesson, but you also won't have to worry about it being on the exam. So that we're a little less cramped. I don't have planned to talk about it in class, but we'll go forward. Actually, this is Monday, Wednesday classes. See, I did take it out, didn't I? Yeah, so we pretty much will be following the same schedule now that we're sort of synced up. We do have fall break in there, so we both Monday and Tuesday classes are closed for fall break. I don't know why they don't do it like spring and give us a full week, but probably because of Thanksgiving. I say they should just take Thanksgiving, give it all. Some of you will take the full week of Thanksgiving off anyway. We'll make that work. Okay, so we'll get to that, and then we'll take another exam, and then we'll do some more stuff, and I think we got one more exam. So there's these 3 exams, and then there's the final that will be over everything. All right, so let's talk about something called the chain rule. I want you to kind of see that we've actually already been doing the chain rule. So what's the chain rule? Well, what's a chain? It's things that are linked together somehow, right? A chain has links and they're connected. And so the connection between these is when we're going to think of functions as being a composite function. So you do these in algebra where you've got one function, you put an input, you get an output, and then you put it into another function that's going to do something. So like in manufacturing, you maybe have a car factory, but at that car factory, they don't make every single part. Some of it's just assembly, right? Steering wheels, they have a special factory to make steering wheels. So there's a function that makes steering wheels. In goes the plastic and the wood or whatever's in the steering wheel, the metal. Out comes a steering wheel. And then that becomes an input to the assembly factory where they have this car without a steering wheel and they put a steering wheel on it. So that's what we're doing. So let me show you that we've actually been doing this. Oh, did I? Yeah, we're recording. Let me forget to get my tools here. There we go. So now, when we did something like, we'll just take a simple one, a function, y equals x to the 5th. And we were told to take that derivative, dy dx, of x to the 5th. What did we do? How do we take a derivative? We take the exponent and multiply. And then what was the next step? And then we subtracted 1. And that's all we really talked about. So we would say we got 5x to the 4th. But I want you to think of the chain rule. There's really one more step that we didn't have to do. But in the chain rule we're going to, there's really one more step. What we also did is we multiplied by the derivative of x itself. What's this would be like x to the first power. So notice we worked with the outside exponent and subtract 1. But what we're also going to do is whatever's in here, we're going to take its derivative. But what's the derivative of just x? 1. So that was 1. So we never talked about it, but we were sort of doing that. And that's all the chain rule is it's doing the same thing, but now we're going to have more than just x in the function. Okay? So we're also going to take the derivative of all that and we're going to multiply by it. But I want you to see that it's not really anything new. We were always doing it anyway, so this was really 5x to the 4th times 1. If you can think of it that way, today's stuff is not anything new. Okay? So I'm going to, I'm presenting it a little bit differently because I've thought through it, and it seemed to go well on Monday. And there was a few things as I was doing it, I think maybe I'll try something a little different. And so you'll let me know if it goes even better today. And the goal was, because they went away, they says, that doesn't seem so bad. And I says, that's what I was shooting for, because for me, it was all about symbols and stuff, and it seemed like it was really complicated. And then when I found out it wasn't as complicated as all the symbols made it, then it was okay. So I'm going to introduce the chain rule. I made some last minute changes, so I might have messed some of these slides up, but we'll fix it up. So what I'm talking about is, notice this is not just x squared anymore, right? This is 3x plus 1, so it's got something more than just x in there, inside the function. So that's what this is about. There's sort of an outside function, something that's going on, and there's an inside function. We have not talked about how to take this derivative yet. But from what I just said, what we just went through, how would you think you would go about taking this derivative? We would look at it as something squared. What would the derivative of that be? 2 times something. And what happens to the exponent? Subtract 1. So I'll put the 1 there just to emphasize that that's what we do. What happened to the stuff inside? Nothing. So it's still there. But like I was saying, now we actually should take the derivative of that inside stuff, right? So what would the derivative of 3x plus 1 be? Well, derivative of 3x is 3. Derivative of 1 is 0. You just did the chain rule. That's all there is. So sort of the thing you have to do is you have to see, I'm just doing the outside stuff, so there's this thing in a parentheses. I just sort of just bring it over, think of it as if it were x, do the stuff with the exponents that we've already been doing, and then the extra step is we multiply by the derivative of this stuff that's more than x now. Okay, that's all there is. What gets confusing is they put all these symbols and they say this is this function and this is this function. They'll separate this one. I think you're going to do better, not like the product rule where we took things apart, took their derivatives, and then put them back in the formula. You'll see, I think it'll work better if we don't do that. But that's what we're going to do. So we'll walk through this, thinking about how would we calculate 3x squared. Well, first of all, we calculate the inside. Right? We would figure out what 3x plus 1 is, and then we would take it to the second power. So if I put in, say, 1, 3 times 1 plus 1, it's going to give me 4 squared, and then the final answer I would think of as 16. Okay, so we kind of work through it that way. And so thinking of it as a composite of functions, and I use I of x for inner, the inside part. And just, I don't know, I run into these things and I wonder about people who write math textbooks. Because I guess, I don't know, it's like they don't live in the real world, because they use, the two functions they use is f of x and u of x. And then, so then the u goes into the f, so it becomes the fu function. And I thought, that's not very polite to put fu for everybody. You know, that's, did they know what that means? Of course, it's just for them, it's 2 letters, but I says, I can't teach that, but I had to at least let you know that I keep running into these things. I says, I don't know. Would you do something different than F and U? So I do F and in. I actually would do O for outside and I for in, but it works, okay? So we've got a function, and so again, the whole part of this is to see that there's an inside part, and the inside is inside parentheses generally, or it could be inside of a square root, but we'll change that square root to a half power. So it's the stuff inside the parentheses, and then we're still doing the same thing, because that's the only way we know, the only thing we know how to take a derivative of is something is x to a power. The power comes down and we subtract 1. That's all we know how to do. We'll move forward and we'll learn about logarithms and exponentials, and those are different. So we'll get some new techniques for it. But up to this point, is just subtracting 1 from that exponent, that's the new exponent, but multiplying by the previous exponent. Okay. And so this is the discussion. Yeah, if you plug 1 in, what you do is you put it on the inside, you get 4, and then you square the 4 and you get 16. So just that's a composite function, thinking of what we're doing. And so that's what sort of makes sense. Again, this is kind of gets wordy. We're just going to look at a few examples, and you're going to see that if just with what you've been doing, taking that derivative, you'll see that inside function, just bring it over, and then you're going to take the derivative of that inside function. Okay. So again, I leave some of the stuff that they do in case you want to go back and read it, because you have access to all these slides. It's in the video, okay, so here's how we take the derivative. And actually, I think they were kind of suggesting you do the inside first, so the derivative of the inner part. I'm going to suggest, as I was doing this, that you take the derivative of the outside first, because that's sort of more natural, and then you've got that inside part, then right next to it, write the derivative of the inside part. So that's how we're going to do this. But again, since it's multiplication, we could do it in either order. So you could do it in whichever order seems to work for you. Some of you might look at it and say, I see the inside part, let me take that derivative. And then I see the outside part now, let me multiply by the derivative of the outside part. Either way will work. Okay, so we'll focus on just taking the outside derivative and then doing the inside. But it's the derivative of the inner function times the derivative of the outer function with the inner function in it as an input. So I think of it as, those parentheses are like a rubber suit. It's a bubble. You can't touch it until you take it out, right? So it's kind of, so the cool part about this is you will always see it. And here again, the symbols in the book, and because it was a screenshot, that's where the FU is, and the derivative of F with the derivative of the inside. And again, if just the notation can get very cumbersome and confusing. So we'll try not to think too much about the notation. Let's just do it. So a quick example, if I think of like we did the inner squared or something like x squared, right? It's really the derivative of x squared is just 2x to the first. But if x is something else, it's really 2 times the inner, and then we have to take the derivative of the inner. And so again, there's the outside derivative. 1 is the derivative of the inside. And that's all we're going to do. But again, we're going to have more than x. So let's get to an example. So here I'm being asked to take the derivative of some function. I've even blacked it out. We'll bring it out. And it's to the third power. So if I think about, I've got something to the third power, how do I take its derivative? The 3 comes down in front, and I subtract 1 from the exponent, right? So it's 3 times something to the second power. And that's all I need. That's half of the chain rule. That's the outside. For the second part, we need to know what's inside there. So we'll show you. So really what's in here? Well, it's just copying whatever was in the inside. And then the second part of the chain rule is to now take the derivative of that inside stuff, right? And we can see, okay, it's right there. So in doing the work, I got what I need, and I just now need to think of what's the derivative of 2x squared plus x. Derivative of 2x squared is going to be, good, 4x to the first, right? Because 2 comes down, there's 4, subtract 1. What's the derivative of plus x? 1. So that's it. We just did the chain rule. Okay, so notice it was just look at that outside, do what we've been doing, and just we're copying it over, and then we've got one more step. Let's take the derivative of the inside stuff. Does that kind of make sense? That's what we'd have to do something like that. Kind of like FOIL. You got to when we're foiling in algebra, we have to multiply everything by everything else. if we're going to take the derivative, and we've got inside and out, we should somehow take the derivative of everything, and that's really what we're doing. So we're taking the derivative of the outside, and then we take the derivative of the inside and multiply it. That might not be real intuitive, but it works because that's what the mathematicians spend, and that's their job. So they say it works, so we just believe them. Because if it didn't work, they wouldn't let us do it, right? So, fine, it works. 2 plus 2 is 4. We accepted that at some place, and we don't question it anymore. We don't ask anyone to prove it to us anymore. There was a time when we probably asked someone to prove that to us, right? But we don't anymore. Derivative times derivative of the outside times the derivative of the inside, it will work. And you'll get to see, and it gives us what we need. Okay, I left this in here. This is the textbook's kind of wordy explanation of what they're doing. Again, if you've got the first part, some of this might get confusing because they do it two different ways, and but they're pretty much saying the same thing, right? We would calculate this. We think of something cubed. They call it the quantity cubed. I just call it something. Something's cubed. And so what do? Again, they took the inner one first, or they're looking at what the inner is. And then they use these, again, sort of substitutions. And that's what always confused me, because it's now they're where did that come from? They just make it up. To me, it's easier just cover it with my thumb and say it's something to the third power, do it, and then move forward. But again, it's in here. You can kind of see this, to me, is more understandable. So what did it do? Well, the 3 came down. There's our subtracted 1. And then that's the derivative of the outside. And then I just now need to take the derivative of the inside to finish it off, just like we did. Okay, so that's all that's going on. And they use some notation here, and they basically did the same thing. They got the outside here, and they said, okay, now take the derivative of the inside, and then they finally do it. They've got a verbal form. The derivative of this cubed is 3 times that thing squared, right? Subtracting 1 times the derivative of the inside. So again, just same thing, multiple ways. And that's because I find is sometimes one thing will click. And again, know yourself. I'm someone that knows this. I wouldn't even look at that stuff, because if I find one way that works, I look at a different way that's going to say, that'll confuse me. So I said, nah, don't listen. Move on. Know what works for you. Other times, I look at the first thing, doesn't help me. So if I look at a second or a third thing, maybe that's what's going to help me. So that's why I provide it there, but I want you to pick and choose and kind of understand what's going to work. So the rest of the examples, we're going to do exactly the same sort of thing. I'm just going to block off the inner. So I got something in a parentheses raised to the 100 power. How do I take its derivative? What do I do with this 100? Multiply it and then subtract 1, right? So we simply have 100 times something in a parentheses. I don't know what it is, and my power is now 99. What's in that parentheses? Well, let's find out. What's behind door number 3, right? X cubed plus x. So I just copy it. I didn't do, again, it's inside the parentheses. It's in a bubble. It's got diplomatic immunity. Can't do anything to it while it's in that parentheses. But what we can do is think of it as an inner side, and we can take its derivative. Because of the chain rule, we're going to have to get to this. So what would it be? X cubed is going to be 3x squared. See, you guys are plus 1. And you see how, as we move forward in this, you're going to get better and better at taking derivatives now. And everything's going to start clicking. And that's what we're going to make sure assess. And we're done. We are done. That is the chain rule. Again, It's going to become even clearer as we'll talk about exponentials and logarithms, and the inside of the function kind of is in a different place with those kind of functions, and the derivatives are going to be different. So we'll have to talk about those, but that's all we have to do is there's an outside derivative, and then there's stuff inside. We got to take its derivative. That's it. That's all there is to it. Again, here's some more wordiness. If you got the first part, I just kind of ignore all of this for now. But if you didn't, maybe that wordiness, or maybe you come back later and read over it. But we took its derivative. We know how to do it. And again, you see, yeah, it's got 100 power. We're multiplying it. We get 99. And then we have to take the derivative of the inside. That's all there is to it. The same thing they did. And some people will ask, do I have to try to simplify this? Well, these ones won't simplify too well. I could take this 100 and I could distribute it over here and here if I wanted to. But what ends up happening is if you algebraically simplify this, you complicate it. You don't simplify because you lose all the evidence of what happened. Right now I see that 100 coming down. I see where it came from. I come back tomorrow or 2 or 3 days later, if I look at my work and if I leave it like that, I know that 100 came from the exponent. And I know that 99 was 100 minus 1, so it's all there. I've got the inside stuff, and then the stuff next to it, I see it's the derivative of that inside. It's all clear. But some of these things, and some of the homework, though, or at least in the examples, they will actually do some of the math to simplify. But as soon as you start doing that, you lose that evidence of what happened. And so when you come back later, where did this 12 come from? I see a 4 and a 3. Oh, they got multiplied, but you got to think through it. But so my suggestion is leave it, especially on your work, just leave it. Don't simplify. Now, if in WebAssign they tell you it needs to be simplified, that you need to take 3 times 4 and get 12 or something, go ahead and do that. But on your work, I would leave it unsimplified. Okay, this one's a little bit more complicated. It's something inside of a square root. So how do we go about taking the derivative of a square root? We always would rewrite it as something to what power? 1/2. I'm going to change it. Is 0.5 the same thing as 1/2? Yeah, and maybe it's a little easier to work with than fractions. So we can do with decimals, right? We can. Except 1/3 is not a nice decimal, 0.333, so that's why, But 1/2 is 0.5, so we could do this. How would we go about taking this derivative? Same thing, right? This 0.5 comes down in front. We subtract 1 from it, 0.5 minus 1. So we're going to get 0.5 times something in a parentheses to the negative 0.5 power. And now let's look what's in the parentheses. Oh, 3x plus 1. That's not too bad. Are we done? No, we need the derivative of the inside stuff, which is not too bad. What's the derivative of 3x? 3. What's the derivative of 1? 0. So 3 is it. And this is where you'll see, I think in the explanations, they will take 0.5 times 3 and make it into 1.5. I said, don't do that, because I don't see where the 1.5 will come from. I'll come back 2 days from now and I'll be confused what happened. If I leave it this way, I'm not confused. I see this 3 and I'm writing it this way. This second part is the derivative of the inside. That makes sense. This 0.5 came from the exponent and I subtracted 1, so I can see it all happening. Okay, I know what happened. And so that's another thing about, like on the test we ask you to show your work. What I say about showing work is it's not so much to prove it to me, but you need to show as much work as you need to. So some of you, maybe you do more in your head. But here's the test, is if you come back 2 days later, are you able to look at your work and know what you did? If you can, then you've showed enough work. Okay. And if on an exam, if you get marked down, then I usually don't, again, if you're getting the right answer, you're going to be fine. But that's sort of, how much work do I need to show? Well, each of us is different. Okay. Sometimes if you're trying to show it for someone else, that's where you make mistakes because you're trying to show too much or something. That's where I make mistakes, but anyway. So that's it. We just did the chain rule again with a square root. And sometimes you'll find that with these, the more complicated it is, they're actually easier because you can kind of see it a little bit. This 3x plus 1 just has the derivative is 3. And again, they'll talk you through it, and I'll just show you here. So see, they actually take that 3 times 0.5 and put 1.5, and I get it. Mathematically, that's the way to do it. But part of math is looking at structures, and if we leave it in that form, we see where everything came from. We see the structure of a chain rule derivative. Especially at the beginning, it'll reinforce it for you. So my thing is to, let's not do this. Let's just stop right here. And I believe WebAssign will give you full credit for these. And again, I may be wrong on some things. I think it does give, if it wants it more simplified, it may give you a message. But again, on your paper, I would leave it this way, because this way, to me, that's gonna increase my learning. And then they even take it further. You got the square root. You could move it down, but you don't have to. You don't have to. And I've seen that it seems like they will take the negative exponents as well. So here we'll go into, we're already ready to kind of go to sort of advanced ones. So we'll get to a few from the homework that might be a little bit of a stumbling block because they have something a little different. So this is from a problem, and this is supposed to be, this is the profit function, and they're going to ask you to get the marginal profit. What's the marginal profit? It's the derivative. Now, do we need to use the chain rule on all of this? Well, the first part, 8x, no, we could just take that derivative. Derivative of 8x is 8. But when we go to this part, we now need to take a chain rule, right? So again, what's the square root? It's the 0.5 power, 1/2 power if you want. But watch how we can move to the 0.5 now, and I'll bet you some of you who maybe were struggling with the fractional part, it'll seem easier to work with. And so how do we take this derivative? The 0.5 comes down in front. The inside stuff stays there, 4x plus 10. We subtract 1 from the exponent, right? So that's now going to be negative 0.5. And then what's the last step of the chain rule? Derivative of the inside stuff. Derivative of 4x plus 10. Derivative of 4x is 4. Derivative of 10 is 0. We're done. And again, if you see this one worked out, they will probably take 4 times 0.5, which is 2. And you could write that. You could simplify. But again, I like this because I can see, where did this 4 come from? Oh, that was the derivative of the inside stuff. Where did this 0.5 come from? That was the exponent coming down. I see it all. Okay, but that's all there is. So there could be some where they're going to give you, and not every term needs the chain rule. Again, this 8 sort of did. We took, it's 8 times 1 if you want to think you could apply the chain rule to it, because you could always take the derivative of x, but it's 1. Okay. This one comes from the Monday class, so someone will say, what do we do with this? That looks like maybe I need to use the quotient rule, right? Because it's a fraction. But I don't need to use the quotient rule because there's no function in the top. There's just a constant. What could I do with this to make it something to an exponent? Not square root. But when something's in the denominator, I can bring it up and put it to the negative 1. Now there's one similar to this that's in parentheses and it's squared, so you'll probably say, oh, just bring it up and put it to the negative 2. Since there's no parentheses, this is what will throw some people. But go ahead, put the parentheses, and then rewrite it as 9x minus 7 to the negative 1 power. Okay. There's always an exponent. Sometimes it's a 1 and they don't show it. They don't show the parentheses. But this is something to the negative 1 power. Now does this look like a chain rule thing? Right? I can see an inside. I can see an outside. And again, we go through this. And again, you'll get it slightly different. But what do we do with this exponent? We take it down and multiply and then subtract 1. It's just the same thing we've always been doing. So that derivative, we'll do it down here. That's going to be negative 1, or just negative. You could do it that way. 9x minus 7. Notice while it's in the parentheses, nothing is done to it. It's got its diplomatic immunity. Can't touch it. But now we take the derivative of that inside stuff. So we're going to multiply by 9. Derivative of 9x is 9. Derivative of negative 7 is 0. That's it. And again, you could simplify it. You could move it back down if you want. But again, I like just leave it like it is. It's correct. If I need to do anything, I can plug it in a calculator. I can graph it. I can get values. I can get my derivatives. I've got what I need. Does that make sense? Okay, so that's, again, you'll see one like this. Just go ahead and put the parentheses, move it up. You'll also see like 2 over something squared. Move it up and make it a negative exponent, just like we've been doing. So far, so good? You ready for a really challenging one? No, me neither. Not too challenging, but it's in the homework, so at least this part will be recorded. We didn't do it in the other class. I just told them, because I didn't see it. I didn't think we'd do it. This one. A little scary, right? But let's just think what we're going to need to do here. Let's not get ahead of ourselves. We see, right? If we just kind of block this off, this is something to the 3rd power. So let's power this out. What would the derivative be? 3 comes down. I guess I shouldn't put equals there. I should go down here. The derivative of this. The 3 is going to come down. Again, don't worry about what's in there. It's nasty, but just copy it. And then what does the exponent become? 2. Subtract 1, we got 2. Got half our work done. Now what do we need to do? We need to take the derivative of the inside stuff, and that's the ugly part. Because that one is a rational function. It's something with a quotient. What do we need to use? Yeah, we need to use the quotient rule. So this is one that takes us back. So, and you're going to start seeing this more as you do it. But there's only one that's this way. Everything else is just really strict. At least I think so. I lied to the other class because I said there wasn't one like this, and then someone showed it to me. I said, really? They gave us one like that? I missed it the first time. But okay, so how do we take the quotient rule? A little practice. This one I'm going to write it here when I'm done. But I'm going to do some scratch work here. Right, I've got a top part, which is 3x minus 9. And I need to take the derivative of the top part. What's the derivative of 3x minus 9? 3. Good. I've got a bottom part, which is 2x plus 6. And I need the derivative of the bottom part, which is just 2. And so the formula, if I take the derivative of a top over the bottom, if I take this derivative, remember, it's the derivative of the top times the original bottom minus the original top times the derivative of the bottom all over the bottom squared. Okay, so now I'm going to take my 4 pieces, I'm going to put them together up here as the derivative of the inside. The derivative of t is 3. The bottom part is 2x plus 6 minus t, which is 3x minus 9, times the derivative of the bottom, which is 2. Squeeze it in. Let me give myself a little more room. And again, you could put the 2 in front of the 3x minus 9, but and then the bottom squared, 2x plus 6. We had something similar on the test like that. I don't think it was any more complicated than that. I'll have to look back, but we did something. And you could just leave it like this. In fact, why should we leave it like this? Because it's got all the evidence. It's got all the work that's been, I can kind of connect it to where it came from. Okay, I can see an outside function, the derivative of an outside function here. Oh, this is a quotient thing. I see the quotient. This has a derivative with the this, and this is this, and I can see it all. And again, when I go back to my notes, I'll be able to see it 2-3 days down the road. I'll see it next week. But if I simplify this out, I'm probably going to make some mistakes along the way too, but it messes it up. Again, what I've got though is I've got something I can put in a graphing tool and I can figure out a derivative from it. I can do anything I need to do with this formula. Simplification is over. It's not that important. In fact, actually, I think sometimes it leads to more confusion than anything else. Just because, you know, so this is just as beautiful as anything. So there's that one in there. If you want to come back and look at that, basically you'll see the same thing. The thing that'll change are the red numbers, which actually don't appear too much in here. So, but take a look at that and just see it, you know. And again, if you want to do some more practice, you can go into the textbook and it'll have maybe a few more like that. But just think the chain rule at this point, we want you to try to look at it as simply as it is. It's just something, derivative of the outside, and then, you know, so cover it with your thumb or something. It's just think of it as x, and then take it off, and then put the derivative whatever in that parentheses. You've got the chain rule. And again, we're going to get more practice because it's going to become more important as we're doing exponentials, and the inside of the function is going to be the actual exponent. Logarithms have an inside part, so we're going to need to know how to take the derivative of a logarithm, which is actually not too bad, but it's usually that there's funky stuff inside. So we're going to be using this chain rule again and again, but it's not too bad. Does it feel sort of okay? Okay, good. That's good. Because that's probably why I had to take calc twice. First time through, I go, what's this? Why do they even call it the chain rule? I don't see a chain. But now I sort of do. And hopefully, again, think of it, it's not that hard. And everybody told me, oh, the chain rule, that's really hard. Actually, it's not. The hard part is they use all these symbols and they put this U substitution and this and that. You don't need it. Just do it. And I think you'll see it more clearly. So do the homework, work on that. I think we take a little bit of diversion. We look at exponentials and logarithms and then we'll start picking back up with this later. So this is Thursday, so Tuesday we'll be back together. We'll look at those and just keep moving forward. Right? Thank you. Plug this in. You could do it a couple ways, but since profit is dependent upon the number of laptops that are sold, and we have that function here, what you can do is you can plug this in for each of the Q's so that the profit function is negative 100,000 plus 5,000 times 30n n squared, and then minus, see if I can be over here, oops, minus 0.25 n squared. squared. What you'll see is they want, so they want now the derivative of the profit with respect to n, the number of laptops. So that's, we've got that function. They want you to plug in 10. So we want to get this derivative. Notice everything else, I mean, I could distribute this. You don't need the chain rule here. The only place we need the chain rule is this little part here. So then you could, again, come up here, take the derivative of p, derivative of 100,000, that's 0. I think I would just go ahead and distribute this 5,000. So that's going to give us 5 times 3 is 15 with 1, 2, 3, 4 zeros. And then 0.01, that moves the decimal over back 2 places, so that's going to be plus 50 n squared. So that's what this part becomes. So we need that derivative. So that's 150,000. That's the derivative of n. N squared, the 2 times 50, gives us 100 n to the first power. Put that, so that took care of this derivative. And then we have a minus, and that's now where I'm going to take this derivative. So I'm going to have 0.25. I have the 2 that's going to come down. I've got the inside stuff that doesn't change. I subtract 1 from the exponent, so it now becomes to the 1 power. And then now this is the chain rule part. So that's kind of like all this long thing. There's only one part that's really from today's that's new. This is going to be the derivative of the inside stuff, which will be 30 n squared. The 2 comes down, so that's 0.02 n to the first power. I'm running out of room. Let me write it down here. So that goes there. And then we plug in 10 for n. So you don't have to simplify any further. Plug in, or whatever your value may be different. But notice it was just really that last part. Yeah. Sure it was. Yeah.